I want to finish out with just a few more items here. So let's say that we were asked to determine if the series from n equals 1 to infinity of n divided by n squared plus 1 converges or diverges. Kind of like we did with our techniques of integration, you sort of develop a flow chart as you start learning these different tests and go through that in a very organized way as you're testing things out. And the first item in that flowchart is definitely to use the nth term test to try that out. But if I look at this expression, it's a rational expression. The degree of the numerator is less than the degree of the denominator, so I know that the limit of that sequence is going to be 0, and the nth term test doesn't tell me anything in that case. So now I will go in instead, maybe try my integral test. So writing that up, we say let f of x equal the real variable function x divided by x squared plus 1. And because we got to compare them and talk about them together, I am going to also name the formula for the sequence as a sub n. So I let that be true. Then, and the order doesn't matter too much here. So I'm going to say, well, what about if I plug in natural numbers there? What if I plug in some natural numbers? Is that going to give me the same thing as if I had my sequence formula? And it does. Then we get into the meat of the matter, which is looking at that function f. So I need f to be positive, and definitely x squared plus 1 is positive for any real number, and as long as I'm talking about x greater than or equal to 1, the numerator is positive, so I know this function is definitely positive. We also know it's continuous, doesn't have any discontinuities in it. But what about the decreasing? In our mind, we of course know that that expression is decreasing. You're dividing by bigger and bigger and bigger. But if we wanted to be really clear about it with someone and prove it, we would actually go and look at the derivative. So the derivative on that, low d high less high d low, low d high less high d low, just 2x. Draw the line down below, denominator squared will go. So if I look at the derivative here, and that gives me 1 plus x squared minus 2x squared is 1 minus x squared divided by x squared plus 1 quantity squared. I know the denominator, of course, is always positive. This numerator, once I get numbers bigger than 1, that is definitely a negative number for x greater than 1. Therefore, I know that f is decreasing. So some professors and the textbook will make you show this work of proving that it is a decreasing function. We really should be able to look at this and understand that it is. So what we now know is that f is positive, continuous, and decreasing for x greater than 1, or what I could write is x greater than or equal to 2. And in fact, at x equals 1, it's 0. So, you know, we could just put a less than or equal to 0 here, and then that would give us the ability to just say greater than or equal to 1 here. If I do that. So that would guarantee that we're decreasing. If the derivative is 0, then technically you're not decreasing, but it's only at x equals 1 that happens. So it's decreasing starting at 1 and continuing. Alright, so now, and I got one more thing. I got to go look at the actual improper integral for f. So looking at that improper integral, meaning the integral from 1 to infinity of x divided by x squared plus 1 dx. I know that that is going to be the limit. We're going to skip a little bit of the steps here. As b goes to infinity, finding the antiderivative, the numerator is almost the derivative of the denominator. I'm just missing a 2. So I'm going to get a 1/2 natural log of the absolute value of x squared plus 1. However, I know that x squared plus 1 is always positive. And we're going to evaluate that from 1 to b, but then take the limit as b goes to infinity. So that gives me the limit as b goes to infinity of the 1/2, I'll pull that out, natural log of b squared plus 1 minus natural log of 2, and that diverges because log of a bigger and bigger number is just bigger and bigger. Even if you're subtracting a finite amount, that's just going to get bigger and bigger. So that diverges. And therefore, the series that I was looking at from n equals 1 to infinity of a sub n, which is the series of n divided by n squared plus 1, also diverges by the integral test. I really apologize for the writing here on this pad, but hopefully it's good enough you can at least follow through it, and I'll be posting these notes, of course. So that's how we prove some of these. We're going to encounter more series later where neither of these two tests works well either. Let's do another example. Looks a lot like the last one, but not quite. So now we want to go here. Again, I'm going to start with the nth term tests, but that definitely goes to 0. 1 divided by n squared plus 1 definitely goes to 0. So I'm going to set up all of this stuff and try the integral test. I have a reason for going through all that again. Oh my goodness. So 1 divided by x squared plus 1, and let a sub n or b sub n or whatever you want to call it be 1 divided by n squared plus 1. Then the function does indeed equal the sequence at all the natural numbers, and I know that f is definitely positive. It's positive everywhere. It is continuous. In fact, that's the Wychwoganski shape. And we know it's decreasing. We're not going to go prove that with derivatives. We know that function well enough. Also, then, I'm going to go look at the definite integral from 1 to infinity. The improper integral of f of x dx. And that means the improper integral of 1 divided by x squared plus 1 dx, which is going to be found by doing the limit as b goes to infinity of the antiderivative at the endpoints of 1 and b. And the antiderivative there is arctangent. So I'm going to evaluate that from 1 to b. So that's the limit as b goes to infinity of arctangent of b minus arctangent of 1. But I know that arctangent of 1 is pi fourths. So as b goes to infinity, the arctangent function, because of that horizontal asymptote, approaches pi halves. So I get pi halves minus pi fourths. I get pi fourths. Or, in other words, this improper integral converges. And therefore, the series converges also by the integral test. 1 a sub n, 1 divided by n squared plus 1. Alright, save myself some trouble here and just type this out. Also converges by the integral test. So the integral test is really nice in that it's a very definitive answer. It'll tell you one way or the other. It tells you converge, tells you diverge. As long as you're able to work out this definite integral, or this improper integral, as long as you're able to work that out, and as long as your function is positive, continuous, and decreasing. So it's pretty cool. By the way, our improper integral converged to pi fourths, but that doesn't mean that our series converges to pi fourths. If I go and look at some partial sums here, I see that from 1 to 10 I get like 0.9818. 0.9818. But then if I go to 100, I get 1.0667. 1.0667. And then I was waiting here to punch 500. It's going to take the calculator a little bit of time here. 1.0747. 1.0747. And now let's try 1,000. Let's say that I try to punch 1,000. Alright, come up here. So I'll do 1,000. That's probably going to take it a little bit of time. $1.0757. 1.0757. So we definitely look like we're converging to a number. However, that's definitely not pi fourths. Pi fourths would be a little bit bigger than 3/4. That's not this number. So even though they both converge or diverge, it doesn't mean they converge or diverge to the same number. Speaking of one particular improper integral, though, we looked at graphs of 1 divided by x to a power, such as 1 divided by x squared, 1 divided by x, 1 divided by x to the 1/2, meaning the square root of x, and we found out that that improper integral converges if p is bigger than 1, and it diverges if p is less than or equal to 1. So 1 divided by x diverges. And so if we have a series that's the exact same thing, except it's given by a sequence on the natural numbers instead of the real numbers, we call that a p-series, and we already know if that converges or diverges. If p is bigger than 1, that is going to converge, and then it's going to diverge if p is less than 1. So that, in a lot of ways, now answers our question back over here about the harmonic series. That is a p-series where p is equal to 1. And if p is less than or equal to 1, that is going to diverge, and this becomes kind of like geometric series. It becomes one where we get to just write an answer almost immediately. So over here we would say, does this converge or diverge? And we would simply say diverges since p-series with p equaling, the power on there is 1/2, and that is less than or equal to 1. So that gives us a super quick way for some series to work with that. However, the one we were dealing with there that had the arctangent, the 1 divided by n squared plus 1, that's not exactly a p-series because of that plus 1. That makes it to where it's not a p-series, but it's definitely similar enough to the p-series 1 divided by n squared that I might have made a guess that I was going to converge, because here this p-series has p greater than 1. So it gives us a little bit of a sense, but unless it's exactly written as a p-series, we'll have to use something else, such as the integral test.